Then there is a biological neuron in our brain. Perceptron is yet another term we might or might not have heard of. There is linear relationship between the number of features and the number of weights that sit on the edges of a single perceptron model. Now the first layer from the left we call an input layer. The second layer from the left we call hidden layer. The third layer from the left we call output layer. So we need something to solve sequences, for which we talked about RNN, and we need something to solve images, which is nothing but your deep computer vision. Hi everyone, welcome to Deep Learning Talks. So in this episode we're going to talk about neural net. So before neural network we do think about the keyword neuron. Now neuron also correlates or connects with something known as perceptron, right? Then there is a biological neuron in our brain, and perceptron is yet another term we might or might not have heard of. I'm assuming you might have heard of something known as logistic regression, right? Because I want to talk about first, where does neural network come from? Like mathematically, academically, and how was it invented? So we're going to discuss all the mental models around neural networks in this video, but let's first start with where does neural network come from? Logistic regression, it's simply y is equal to mx plus c, a linear equation, right, on top of sigmoid or encapsulated under sigmoid, right? So logistic regression itself comes from linear regression, which is y is equal to mx plus c, right? Now when we top off y is equal to mx plus c with a sigmoid, and it's basically weighted average of all the inputs, and along with a bias, along with an activation function, which is logistic, right? And the loss function obviously is different than linear regression. The loss function that we use is binary cross entropy loss. In linear regression we generally use mean squared error, right? So a single perceptron is nothing but a simple logistic regression model. You can correlate it with a logistic regression. A single perceptron also has equation which is known as y is equal to mx, right? And if you look carefully at the architecture of a perceptron, it's a simple neuron and has a lot of incoming edges. All those incoming edges are nothing but the input is coming from the left, and it's joining or getting connected to a neuron, right? That neuron is known as a perceptron. Now on every edge that the input is coming on, weights is something that sit on every edge, right? So on every edge we'll see weights, right? And on every neuron we'll see bias, right? So that's why we do weighted average of the input. Weighted average of the input means the weights get multiplied with n and bias get added in that weighted average, right? That's why we call it wx plus b or mx plus c, or weighted average of, right? So the summation operation, the linear operation that happens in a neuron is basically the summation operation. We just sum all the input along with the weighted edges along with the weights and add a bias, which is nothing but weighted average. The summation operation is what happens on a neuron. Now on this summation operation we also apply some form of nonlinearity, which is basically the activation, right? Now the neuron produces something which is known as an output, right, or y hat. Generally every output we talk whenever we talk about output, we correlate it with the keyword y hat, right? So we have two y's, y true or y hat, right? So there is a true variable, there is a predicted variable. So y hat is your predicted one, right? So in supervised learning we have truth labels. In supervised learning we also have pred, or which is the y pred or the predicted variables, right? So neuron takes an input, produces out, right? So it is also encapsulated in a function f of x or g of x, whatever you want to call it, and it simply does weighted average of inputs and adds a bias. This summation operation then gets followed by a non-linear activation, right? Now depending on your use case you might be using different activation functions. So we have different activation functions that you might have heard of, like ReLU, sigmoid, softmax, right? So now this is nothing but a perceptron, right? A perceptron can directly correlate with a logistic, because a logistic regression is also one equation, right? Let's say I have f amount of features, I will have f amount of weights, right? Each w1 will get multiplied with each with each input along each feature, right? So it's not non-linear amount of features, right? There is linear relationship between the number of features and the number of weights that sit on the edges of a single perceptron model. When we talk about neural network, we stack horizontally and vertically all of these neurons and connect them together in a dense form. Now, you will have to look at the architecture of a neural net. In that architecture, you will see we have a lot of vertically stacked neurons in one layer. Then we have another layer which has a lot of vertically stacked neurons. Then we have another layer which have vertically stacked neurons, right? Now the first layer from the left we call an input layer. The second layer from the left we call hidden layer. The third layer from the left we call output layer, right? So what exactly is the input layer? The input layer is simply basically that takes in a lot of input, right? If there are 10 features that we are dealing with in a tabular data, and we're building a neural network to classify that data, to solve a classification problem under that data, we will have 10 input neurons. Hidden layer, let's talk about it at the end. But output layer, let's say we are solving a binary classification problem using a neural network, we will use 2 neurons. Simple. In the output layer, number of output classes correlates with the number of output neurons. Now, hidden layer is basically a hyperparameter. Hidden layer can have X amount of neurons, right? And that is the choice of the trainer, the choice of the scientist, the choice of the developer. That's why we call it a hyperparameter, right? We can have multiple hidden layers. We can have multiple neurons in the hidden layer. The hidden layer is basically adding more and more complexity in the model. Now, what really happens? Why do we need complexity? Because the data that we're trying to model is highly we need a model. There is complexity in the data. We need a model to be able to exhibit that complexity, to be able to express that complexity, and to be able to produce results and inferences on that complexity. In simple words, we also call hidden layer is helping us make a nonlinear model, or hidden layer basically, the more and more hidden layer basically adds more and more complexity in the model, right? Because there is already complexity in the data. We need the ability to exhibit, to express that nonlinearity and complexity, right? So more and more hidden layers, more and more model complexity. More and more hidden layer, more and more model complexity, more and more variance, and maybe higher chances of overfitting in the model, right? So there are different repercussions, but let's try to first understand the concept of hidden layer, right? Now, the main idea that we talked about is the architecture, which is we talked about input layer, hidden layer, and output layer. This is the mental model that you should learn to understand the architecture of a neuron, right? That it has input layer, it has hidden layers, and it has output layer. Now, once you've understood, okay, so we kind of know that the default architecture of a deep neural network does not solve everything around image modality. It fails to capture the spatial relationship between the pixels. For example, if there is a pixel patch that is representing the left eye in a facial image and the pixel patch that is representing the right eye in the facial image, the neural network does not by default know that both of these eyes are symmetrical objects and they are, placed right next to each other. It does not have any spatial spatial, any spatial information, right, with respect to image. Same with sequences. It does not preserve any meaningful relationship in the sequence, right? It fails to capture the relationship between recurring sequences. It does not really know which word is coming after which word. It does not have the idea of positional encodings or positions and orders of a neural network. It cannot do subtraction on its own, so that it can calculate the position of x and position of x minus 1, that they're only 1 unit apart, and it does not process each thing using a sequence window. So we need something to solve sequences, for which we talked about RNNs, and we need something to solve images, which is nothing but your deep computer vision or deep vision modeling or computer vision that basically encapsulates everything that we have in CNN. Right now, we have CNNs, which is a natural extension to a neural network. We have RNNs, which is a natural extension to a neural network to solve text, right? So naturally, where does it sit on the deep? We understood the hierarchy. The downstream dependencies of learning a neural network allows you to learn everything about logistic regression. Now, logistic regression is dependent on linear regression. Now, linear regression itself is a very simple, efficient algorithm that is built on top of simple algebra. If you want to extrapolate it to matrices, to higher dimensional data, you need to learn linear algebra, right? So the downstream dependencies is very simple. To learn neural networks, learn logistic regression. Before that, learn linear regression. Before that, learn simple algebra and linear algebra, right? And obviously, you need to also learn all the ancillary things in the vicinity, which is the activation function, different types of loss function, and the idea of gradient descent. Because the structure is the same. The structure of solving a problem using logistic regression, the structure of solving a problem using a neural network is very similar. Right? We have gradient descent that will help us do back propagation. We have activation functions that will help us add nonlinear. We have loss function, which will help us define the objective of a problem. Right? Now, the forward pass is what changes. Right? What changes in the forward pass? Logistic regression had simple y is equal to mx plus c. Now we will have cascaded y is equal to mx plus c because we have multiple layers, right? Y will have mx plus c obviously, but m's and x are going to be a little. We will not have smaller number of m's. We will have a lot of parameters, right? The number of learnable parameters, the trainable parameters drastically increase in neural network when you compare it with the logistic regression, because we are adding more and more stacks of logistic regression, right? We are adding more and more units of neurons or perceptrons, and we are horizontally stacking them and vertically stacked to build a neural net, right? So the forward pass gets a little more complex. Now, if the forward pass is getting complex, obviously the backward pass will also get complex. But the mental model to understand gradient descent is sim. Differentiate the loss function with respect to all the parameters to get their optimal value, to get their optimal gradient value, so that you can use the update rule to optimize, right? So that remains the same. The idea of forward pass also remains the same, right? The idea of backward pass also remains the same. The idea of activation functions and loss functions also remains the same. Now, why it's relevant? As we talked about, that we have extended neural networks to recurrent neural networks, to convolutional neural networks, to generative adversarial networks, and now we have transformers that sit on the shoulders of recurrent neural networks networks, not exactly on the shoulders of vector neural networks, but they've solved a lot of problems that RNNs were facing. They have solved a lot of problems that traditional neural networks were facing, right? So all the modern language models that we see, all the modern transformers that we see are nothing but some sort of feed forward neural network paired with more and more complexity, right? Some neural networks we have paired with the idea of convolution to solve images. Some neural networks we have paired with the idea of recurrences to solve sequence models. Some neural networks we have paired with the idea of attention to capture contextual relationship and to do next token prediction, right? So this is the main idea of a neural network, and this is how to build an opinion on neural networks and how to learn neural networks. What are downstream topics that we should know to understand neural networks and why neural networks are super relevant. Thank you.